All right, hello 7th math students. This week we're getting into probability of compound events, but we are finding it a different way than we found it last week. So last week we actually listed out every single possible outcome, and then we were able to see how many favorable outcomes there were and how many total possible outcomes there were. Now we're not going to do that. Sometimes there's too many possible outcomes to list out every single one. So we're not going to do that. Instead, we're going to do it another way. Now, we first have to talk about there are two different types of compound events. There could be independent events. Independent meaning the two outcomes are completely separate. So the two events you're doing, they're not going to affect each other in any way. So if I am playing a game and I have to spin a spinner and I also have to roll a die, well, whatever I get on the spinner, that's not going to affect how I roll my die, okay? It's not going to affect the outcome of it. So those are independent, okay? What we do then is simply take the probability of the first event, so this is what that capital P and then parentheses A, and then we multiply it. I know it's really tiny here, there's a dot, so keep in mind that's a multiplication sign, by the probability of the second event, so B, okay? Now, sometimes, let's say we're playing a card game and I pick a card and then this person sitting next to me also has to pick a card right after me. Well, depending on what I drew, now the probability of the person next to me has changed because now there's not as many cards in that deck, if that makes sense. So the outcome of the first event of me drawing affects the probability of the next person. So that is called a dependent event. Okay, and I'm going to try and keep my colors consistent here so that each example I do, I will do either orange or green to show you which one's independent, which one's dependent. Okay, now the same thing happens here. We're still going to multiply the first event by the second event. Again, this little dot in there, that is a multiplication symbol. But the difference here is B following A. Our bottom number and our top number and or may change depending on what happened in the first outcome. Okay, hopefully this makes a little more sense when we do some examples. So example 1, find the probability you will roll a 6 and then a 5 when you roll a die twice. So let's think about this. If I pick up a die and I roll it, I get a number, okay? If I pick it up again, does that first thing that happened, is that going to affect the second roll? Those are completely separate things we're doing, okay? We're picking up a die, rolling it, picking up again, rolling it again. So these are independent, okay? So I'm going to highlight this in orange to show you it's independent, okay? So when we find this, sometimes you will see this as a capital P and then in parentheses, what are we finding the probability of? Well, we want to roll a 6 first, and then we want to roll a 5. Okay, so to figure this out, we're going to figure out, well, what's the probability of rolling a 6? And then we're going to multiply it by what's the probability of rolling a 5. Okay, you guys were really good at this when we were back at school, so the probability of rolling a 6, remember, think about favorable, so how many 6s are on that die? Well, there's 1 6 out of a total of 6 numbers. Okay, and then we're going to multiply it by probability of rolling a 5. Again, there's only 1 5 on that number cube and 6 total numbers. Okay, so we'll just multiply those. And multiplying fractions, we just multiply straight across. So 1 times 1 is 1, and 6 times 6 is 36. Okay, so there is our final probability that is simplified. Okay. Example 2, a bag contains 3 red marbles, 2 green marbles, and 4 blue marbles. 2 marbles are drawn randomly from the bag and not replaced. Find the probability that both marbles are blue. So that means we want to reach in this bag, we want to pick out a blue, and it says here the marble is not replaced, so we're not going to put that marble back. Think about that. In our bag now, has something changed? We have less marbles in there. So the second probability of picking a blue, well, we have one blue in our hand, and there's one less marble in the bag. So this is an example. I'm going to highlight it green because this is a dependent example, okay? And I'm going to change this because this is our key phrase, not replaced. If you ever see something that's not replaced, it is a dependent example, okay? So what we're doing, we want to find the probability of both marbles being blue, okay? Sometimes you'll see probability written out like that. So let's think of the first event, so the first probability of it being blue, okay? How many blue marbles are there, okay? You don't want to, I often see mistakes of, oh, well, we just need one blue marble, so that's our top number. No, remember, it's favorable. How many blue marbles could we possibly draw from the bag? So there's 4 blue marbles in that bag out of a total of, we have 3, we have 2, so 5, and 4, so we have 9 total marbles, okay? Now we're going to multiply that by the probability of the second one, but this is following. We always expect that the first event happened. So right now I have a blue marble in my hands, okay? How many blue marbles are left then in that bag? Well, there was 4, so now there's only 3 marbles in that bag, okay? Now we started out with 9 total marbles, but I have 1 blue marble in my hand, so when we go to draw that second marble, there's only 8 possible marbles in there, okay? So this is how you can kind of see those bottom numbers changed and the top numbers changed. So that's a dependent example, okay? Now again, with multiplying, we just multiply straight across. 4 times 3 is 12. 9 times 8 is 72. Now both of these are even, so I know that we can simplify it. And I think 12 actually goes into 72 maybe? 6 times, I'm pretty sure. Let's say we divide them both by 2. Just doing this in my head. So we'd have 6 over 36. Yep. And then 6 and 36 can both be divided by 6. So we will get 1, I'm going to go down here, 1 over 6 as our final probability, okay? And I don't mind, guys, you are more than welcome to plug this into Desmos. Oops, I don't have Desmos pulled up. And I'll show you guys, if you didn't know with fractions, you can actually type in the fraction times the fraction. So we had 4/9 for our first, and then multiply it by 3/8. Now you're going to get a decimal, but if you hit this button over here on the side, it changes it to a fraction. And there you go, 1/6. Okay? All right, let's keep going. Uh-oh, I hope that other part saved. There we go. All right, down here, a bag contains 3 red, 4 blue, 6 yellow marbles. 1 marble is selected at a time, and once a marble is selected, it is not replaced. There's that key phrase there, so we know this is a dependent example. And 1, 2, and 3 all go with this example, okay? Find each probability. So the probability that 2 are yellow. So the probability of the first one being yellow, okay, again, think about how many yellow marbles are there. There's 6 yellow marbles. So 6 out of, how many total do we have? We have 3, plus 4 is 7, plus 6 is 13. So 6 out of 13. Okay, then we're going to multiply it by the second marble being yellow. Now again, remember it said right here, not replaced. So we're assuming we have a yellow marble in our hands. If there were 6, well now there are 5 yellow marbles. Okay, there was a total of 13 marbles in the bag, but now we have that yellow marble in our hand. There's only 12. Okay, and we can multiply those. I'm going to go ahead and jump over to my Desmos. So 6 out of 13 times 5 out of 12. Switch it to a fraction. We got 5/26. Okay, and I'm just doing this to save time. remember, guys, we can multiply straight across, okay? Let's look at the next one. So the probability that the first one is red and then the second one is yellow, okay? So probability of the first one being red. How many red do we have? And right now we're starting a new problem, so all the marbles were thrown back in the bag, okay? So we have 3 red marbles, and we know there was a total of 13, okay? Now, probability of yellow. Think about, we have a red marble in our hand. So did the yellow marbles change at all? No, we have red in our hand. So there's still 6 yellow marbles. So this one's a little different than the last 2 examples. But the bottom number, did that one change? Well, we had 13 marbles. We have a red marble in our hand. So yes, we have 12 marbles. Okay. Personally, I'm a big fan of simplifying in multiplying fractions or using cross products. So 6 over 12 is the same thing as 1/2. And then we could multiply straight across. I don't even need my Desmos for this one. 3 over 26. Okay. That last example, guys, remember we talked about cross-canceling. If you look at the diagonals, so 6 and 12, it's just like simplifying a fraction. So 6 and 12, 6 goes into both of them. So 6 divided by 6, 12 divided by 6, and then we can multiply straight across. 1 times 5 is 5, and 13 times 2 is 26. It works out, okay? Last example then. So now we have 3 things that are happening. We want to pick a blue marble, then a red marble, then a yellow marble. So we're going to multiply, again, all 3 of these, and all 3 times none of the marbles are being replaced, okay? So the probability, the first event, of the blue marbles. So we have 4 blue marbles, that's our favorable, out of 13 total marbles. Okay, now think about it. The first event happened. We have a blue marble in our hand. So how many red marbles are there? Well, those didn't change. We still have 3 red marbles. Okay, however, our bottom number, we had 13 marbles to start with, but we have a blue one in our hand. So now we have 1 less. We have 12. Okay, now probability of the yellow. We now have the first 2 events happen. We have a blue and a red marble in our hands. Okay, so how many yellow are there? Well, that didn't change. We still have 6 yellow marbles. Okay, however, there's 1 less in the total because now we have 2 marbles in our hands, so there's 11. Okay, and we can multiply all of those. Again, let's see what I could do. 3/12, both of those can be divided by 3. And I think that is all. I don't see anything else that we can do. So 4 times 1 times 6 is 24. I am not going to be able to do 13 times 4 times 11 in my head. So let's do 13 times 4 times 11. 572. Now, both of those are even, so I know I can simplify. So let's just 24 divided by 572. I'm saving some time here. 6 over 143. So looks like we could divide both of those by 4. Yep, that works out. Okay, so there's our final probability of all 3 of those events happening. Okay, I'll do a few more here. George has 2 red socks, 2 white socks in a drawer. What's the probability of picking a red sock and then a white sock in that order again if the first sock is not replaced? So this is dependent. All right, so we have, we're looking for a red sock and then a white sock. So the probability of the first one being red, second one being white. Okay, so probability of it being red, well, we have 2 red socks, so favorable is 2 out of a total, if we have 2 red, 2 white, 4. And then the second one, so we have a red sock pulled out of the drawer, so the white socks didn't change. There's still 2 white socks, but now there is 1 less sock in the drawer. So we can multiply these. 2/4, I'm going to simplify to 1/2. If we look at the diagonals here, the 2, 2, we can divide both those by 2. So I'm going to cancel them out again. And then 1 times 1 on the top, 1 times 3 on the bottom. So it is a 1/3 chance. Okay? If you don't like that cross canceling, guys, no big deal. I like to do it just because it makes your numbers smaller. But if you did 2/4 times 2/3 and you just multiplied straight across, 2 times 2 is 4, 4 times 3 is 12, and then both of those can be divided by 4 to get 1/3, and look at that, it's the exact same answer. Okay, so you can do it either way. Okay. Phyllis drops a penny in a pond, and then she drops a nickel in the pond. So what's the probability that both coins land with tails? Think about this. If you drop a penny in a pond, okay, and then you have a nickel in your hand, is the outcome of the penny going to affect the outcome of the nickel? No, those are two totally separate things happening. So the nickel in the pond, penny in the pond, and then the nickel in the pond, I'm highlighting them orange because that is an independent thing. They're totally separate. Okay? So, probability of both tails. Okay? So, let's think of the first thing, the penny. What's the probability of the penny being a tails? Well, there's one tail out of 2 possible outcomes, either heads or tails. Same thing with your nickel. There's 1 tails out of 2 possibilities, heads or tails. Okay? Multiply across, 1 times 1, 2 times 2. The final probability is 1/4, or remember we talked about, that's 25%. Okay? A die is rolled and then a penny is dropped. So if you roll a die and then you drop a penny, does the outcome of the die affect the outcome of the penny? They're two totally separate things again, so this is independent, okay? Find the probability of, let's see, we want to roll a 2, and then we want tails, okay? So think about a die. How many 2s are on there? Well, there's 1 2 out of 6 possibilities, okay? Your penny, the probability of flipping a tails, well, there's 1 tail out of 2 total outcomes. Multiply straight across, 1 times 1, 6 times 2, so 1/12 is your probability. Okay, so I did all of those examples for you. All of those examples should be saved in Shobi if you want to go back and look at them. You have 10 questions on Quizizz. Please don't hesitate to ask me if you have questions. You can do that as many times as you want. I will take your highest score. All right. Thanks for listening, guys. Hope you have a great week.